Hi grade 12s, we're on to the third video of sketching rational functions within AP Maths. So far we've sketched linear divided by linear and we've sketched quadratic divided by linear. We've noticed that they don't necessarily have a set pattern, not every one of them is the same, but we do start to pick up, a trend. So we're on to this, actually what is the 7th example, so pardon my typo. And the next typo which I've seen in all my questions is that I'm missing the name of the function. So draw a graph of f of x equals x cubed minus 4x squared over x squared minus 3x minus 4. So this is a cubic divided by quadratic, which is going to be our next couple of questions. So the first thing I always ask myself in any function, can you factorize and simplify? So in this particular question, if I factorize out the top, I take out a common x squared, which leaves me with x minus 4. And if I factorize the bottom, I get x minus 4, x plus 1. Now that means that your x minus 4s are going to cancel. And the moment I do that and simplify to x squared over x plus 1, I notice I'm actually drawing a quadratic over a linear, except x cannot equal to 4. So the moment something cancels away, this becomes a removable discontinuity. And I can figure out the y value at this discontinuity, because if I just substitute 4 into my simplified version, you'll get 16 over 5, which is 3,2. So that's my removable discontinuity. So actually this pattern that I'm hopefully going to draw, I should maybe recognize, because we've drawn quadratics divided by linears in the past. Okay, I always prefer to do my asymptotes next. If you notice, I have a denominator which is left over, so that means x is equal to negative 1 is my vertical asymptote. And finally, this is the degree on the top is 1 more than the degree on the bottom, so there is going to be an oblique asymptote. And so for my oblique asymptote, I say, right, x squared can be rewritten as x plus 1 multiplied by something. So it'll have to be x times x, which will be x squared plus x. Now don't forget, I need to be accurate to a degree of 1 less than x squared. So my x's in this case need to be accurate, and currently my x's are not accurate. This should be x squared. I want to get rid of the plus x, so I'm going to minus x, which means this needs to be minus 1. Unfortunately, that means that there's now a minus 1, which I don't want, and so I need to plus 1 in order for this to work out. So if I now simplify this entire thing, I should get x squared minus 1 plus 1, so actually just simplifies to x squared. So that's good for me. Now, if I have a look, this is not equal to 0. 1 cannot possibly equal to 0, so that remainder can't be equal to 0. Therefore, the graph will not cut the oblique asymptote. If it did cut the oblique asymptote, I need to label that point. So this is really important. So the graph will not cut the oblique asymptote. Now, what actually is my oblique asymptote? Let me just write that down. My oblique asymptote is y equals x minus 1. So therefore, y is equal to x minus 1 is my oblique asymptote. Don't forget that if they just ask you to draw this, then they're not actually marking any of this working, and so you can write less of these notes. You just have to work things out. Okay, we've simplified, we've found our asymptotes. I would then prefer to find my intercepts. My x-intercept is pretty obvious, because basically the only thing that could possibly equal to 0 is this numerator. Watch that I'm always going back to the simplified version. There's no need for me to go back to the original every time. So when does x squared be equal to 0? Well, that's at 0. So 0, 0 is the x-intercept, which means my y-intercept must also be at 0, 0. Again, you could go and sub in 0 to check, but the moment your x-intercept is at 0, 0, your y-intercept is at 0, 0. So the last thing I need to do is I need to find my stationary points. Now again, to find my stationary points, I need to differentiate, but I would go to the simplified version. There's no need to go back to the more complicated version. It just makes a really, really messy equation. So that is my simplified version. So the quotient rule says differentiate the top, multiply by leave the bottom, minus leave the top, differentiate the bottom, all over the bottom squared. Now I have to write that bottom squared, but we've discussed before that the moment I make this equal to 0, that bottom is useless to me, because I just multiply by it and it disappears. So actually the numerator is the only thing I'm interested in, so it's 2x squared plus 2x minus x squared. So 0 equals x squared plus 2x. Now, this is AP Math, so we definitely don't show factorizing. We either put that in our calculator or we do it in our head, but I get x is equal to 0 or x is equal to negative 2. So as a coordinate, we know that's 0, 0. If I substitute negative 2 into my simplified version of my function, so x squared of x plus 1, I get negative 4. Now, before I even go anywhere near working out points of inflection or anything like that, I would plot what I have so far to see if we can make head or tail of it. So what do we have so far? Well, here's my axes. Don't forget that because you're going to be drawing asymptotes on the same graph, you do vaguely have to have some sort of scale. So if this was negative 1, I would have a vertical asymptote at negative 1. So x is equal to negative 1. My intercept is at 0, 0. My oblique asymptotes, I like to draw them first, is y is equal to x minus 1. So if this is minus 1 and this is 1, it would go straight through those two. Don't forget to always write the equation. So this is x minus 1. It goes through there. So I know that this is my stationary point and my intercept. Now negative 2, negative 4. Now negative 2 will be about there. This point will be at negative 1, and if I sub negative 1 into my oblique asymptote, I get negative 2. So I know that at negative 2, negative 4 will be somewhere down here. So that's negative 2, negative 3, somewhere down here. It doesn't have to be completely accurate, but where it is placed in relation to the asymptotes are important. Now, we have drawn this idea of a quadratic divided by a linear before, and we saw that it tended to be kind of like a bit of a squished hyperbola. So this is starting to make sense because negative 2, negative 4 is a stationary point, and I need to tend towards the asymptote and tend towards the asymptote. So that kind of seems to make sense. If I look at the other side, this is a stationary point. Now, I cannot possibly go down, as we said in the previous video, because I don't cut the oblique asymptote. So I pretty much have to go up. And again, because I don't cut the oblique, but I have to tend towards it, I'm pretty sure that it has to be something along the sides. Now, why I haven't continued there is, don't forget I have a removable discontinuity. And that removable discontinuity is at 1, 2, 3, it's at 4. And it must be above here, because it can't be anywhere else. And so that was 4, and it was 16 over 5, if my memory serves correctly. So obviously I haven't drawn that particularly accurately, but that doesn't really matter as long as the placing is fairly accurate. And so I've got a removable discontinuity there. And again, we've seen this pattern before, so this makes sense to us. Those two stationary points are stationary points. So I've got my intercept, and that looks really pretty. We're starting to become more comfortable with this type of shape. So that was fun. Okay, now how to get even more fun is this next example. This is very cool. A cubic divided by a quadratic again. Draw the graph of, now let's do my typos first. This is actually example 8, and let's call this Freddy. And there's my question. Now, again, can you factorize and simplify? Even if you can't simplify, factorizing is a good idea because it helps you see your intercepts. Now, I definitely would not factorize that manually. You have a calculator in AP Maths for a reason. So I put that in my calculator, and I've got negative 4 as a root, which means x plus 4 is a factor. And I've got negative 1 as a root, which means x plus 1 is a factor. Now, when I pushed equals, it went back to the question. Now, that means one of these factors is repeating. So if one of these factors is repeating, we have a problem, because which one? Now, it's very easy to tell by inspection which one. Either this is x plus 1 or this is x plus 4. But if I look at my constant, there's no way my constant can be 4 times 4. And so I know that this has to be plus 1. So a little bit of a trick there, and don't forget that it's easily solvable. And this is divided by x squared. So can I factorize and simplify? Absolutely not, which means there's no removable discontinuities here. Let's go on to my asymptotes. My first asymptote is the fact that x is equal to 0 is a vertical asymptote. Notice it's x squared, so that's interesting. we've never had a repeated asymptote here. So is that gonna mean something? So let's hold on to that thought. My oblique asymptote is going to exist because the top has a degree 1 more than the bottom. So x cubed plus 6x squared plus 9x plus 4 is equal to x squared times by something. So it must be x squared times x. Now, don't forget that you need to be accurate to a degree 1 less than the fact that this is x cubed. So I need my x squares to be accurate. Now, so far all I've got is x cubed. So my x squares are not accurate. So in order to make my x squareds accurate, I need a plus 6. So that this is now plus 6x squared. So now this is accurate and accurate, so that's good. So what's my remainder? My remainder is the fact that I need plus 9x plus 4. Now we have yet to see an example like this in sketching. This remainder can equal 0. So wherever 9x plus 4 equals 0 will be the point where this graph is going to go straight through the asymptote. So at x is equal to negative 9 over 4, my graph will cut my asymptote. Now I'm quickly going to work out my y value because this is going to be a really important point and we must plot it. So to plot the y value, I'm just going to sub in x into the original and work it out. Now I got 50 over 9. Now I don't really know what 50 over 9 looks like, so I'd prefer to write it as a decimal possibly. So let me just write myself a note here that this is 5,555, so 5,56. Great, so that's very interesting. We've never had that before. So I still haven't finished this kind of note here because where's my oblique asymptote? My oblique asymptote is at y is equal to x plus 6. So as x tends to infinity and negative infinity, I will tend towards that, but not, I will be going straight to that asymptote at a point. Okay, great. Second last thing, my intercepts. My x-intercepts are very easy to see because I've already factorized. So it was at negative 4, 0, and the other one was negative 1, 0. Now, again, this was a repeated factor, and I'm pretty sure that when we did cubics, we said that when something was a repeated factor for an intercept, it happened to also be a stationary point. So it's going to be interesting to see if that trend still holds here. So the last thing I need to do is to actually go and find my stationary. Oh, well, no, I haven't found my y-intercept, so let's pause. My y-intercept would be when x is 0. So, interesting. Can you make x 0? Absolutely not, because it's one of my vertical asymptotes. So basically, scrap that. No y-intercept, because x couldn't be 0. So now finally we're on to our stationary points. So let's go and find our first derivative, which is going to be interesting because this is quite a complicated function. So differentiate the top. So that's 3x squared plus 12x plus 9. Multiply by, leave the bottom. Minus, leave the top, x cubed plus 6x squared plus 9x plus 4. Multiply by the derivative of the bottom, which is 2x, all over the bottom squared, which is actually x to the power of 4. Let me write that a bit better. That's x to the power of 4. Now don't forget, the moment I make this equal to 0, that is no longer, that denominator is pointless, so I'm going to leave it out. So I actually get 3x to the power of 4 plus 12x cubed plus 9x squared. Now, it's around about here where you start thinking you've gone wrong. Don't worry. Minus 2x to the power of 4 minus, not a plus, minus, let's get that right, minus 12x cubed minus 18x squared minus 8x. So don't worry when this is looking absolutely hideous. 3x to the power of 4 minus 2x to the power of 4 is x to the power of 4. 12x cubed minus 12x cubed disappears. Then I get minus 9x squared and minus 8x. So that's why we didn't need to actually panic here, as far as I can see, because x is actually going to be common. And so I actually then get x cubed minus 9x, x cubed minus 9x minus 8, and I have a calculator. So I can simply just solve this by picking up the calculator. So I get negative 2,37 by using my calculator, or I get x is equal to 3,37, or I get x is equal to negative 1. Now, a couple of things to pick up here. First of all, remember we said that the asymptote was repeated. Interestingly, that asymptote was at 0. So x is equal to 0 cannot possibly be a stationary point here because it's an asymptote. Also notice that didn't we predict that x is equal to negative 1 would be a stationary point because it was a repeated x-intercept. So that same trend that we spotted when we started drawing cubics in normal maths is the same thing that's happening here. So we actually have 3 stationary points, which is pretty cool. Now we haven't worked out the y values of these, so very importantly, this is negative 2,37 and its y value. I get a y value of 0,54. The other one is 3,37 and I get a big y value of 12,39. And finally, I know what negative 1 is. This is negative 1, 0. Okay, now this doesn't seem to make any sense, and where does this actually look like? And so actually the best place to now is just to start drawing, and slowly things start to become apparent. This is probably one of my favorite graphs. It's really quite cool. Okay, so first of all, I think we tend to forget the asymptote if it's on an axis, so I'm actually going to deliberately draw an axis here. I'm just kind of reminding myself that x is equal to 0 is one of the axes. Then my oblique asymptote was y is equal to x plus 6. So as I'm just going to say minus 6 there and plus 6 there. I'll have to figure out my scale in a moment. So if this goes through here, this is y is equal to x plus 6. Now you just kind of start plotting intercepts to see how it goes. So my one intercept was at negative 1, if my memory serves. And my other intercept was at negative 4, so that's somewhere down there. Okay, so that's an intercept, that's an intercept. This negative 1, don't forget, is also a stationary point. So this is a stationary point. This is just an intercept, so I shouldn't actually color them the same, so let me change that. This is a stationary point, so let's make it green. Now, where were my other stationary points? My other stationary point was at negative 2,37, so that's somewhere there, and it's at 0.54. Now, do I think it's above the asymptote? Do I think it's below the asymptote? Well, maybe I should draw in the point where my graph cuts the asymptote. So my graph cuts the asymptote, if you remember, at negative 4/9 and 50,9. Now, negative 4/9 is, a little bit less than half. So actually, that'll be somewhere there. So my graph is going to cut my asymptote at that point there. So I must label it. This is negative 4/9. And this was, I think, 5,56 if you rounded it to 2 decimal places. And so that kind of makes sense because it's just below the y-intercept of that asymptote. So that's pretty cool. So obviously, even if I don't actually work this out, negative 2 and negative 2,37, I shouldn't actually write negative 2 there, then this will be negative 2,37 and 0,54. It must be below, even though I haven't really checked, it has to be below the oblique asymptote because this graph can't touch the oblique asymptote. Now that is a stationary point, which pretty much shows me that I have to be turning there. I can't be stationary and going up. This pretty much looks like it has to do this. Now remember, you don't really know what this looks like. You kind of just have to figure out what it's forced to look like. So it's pretty much forced to. Now that looked a little bit terrible, so let's try again. This is a stationary point, and then I have to go through here. So clearly, I think this must go up through the asymptote and tend towards the vertical asymptote. This must be a stationary point through the intercept and tend towards my asymptote. Now that's a pretty cool graph. Now I think that covers, if you just look at that, I think that makes sense because I've got my x-intercepts, I've got my stationary points, I'm going through my oblique. That's pretty cool. Now the only problem is I haven't drawn the other part of the graph. So what's the only other thing I know is I know that it has a stationary point at 3,37 and 12,39. Now to figure out where that is, if you put 3,37 in there, you would get 9,37. So basically, if you plotted 3, this would be 3, 0.37 and 9,37. So I must be above the oblique asymptote. So this is 3,37 and 12,39-ish. I mean, I haven't drawn it. And for a lack of being able to draw this, let me just erase this so I can draw nicely. If that's a stationary point, I have no other places where I'm going to cut the oblique asymptote. I have no other intercepts, so I'm pretty much forced to draw this like a bit of a hyperbola. It's going to tend towards the vertical asymptote, which is there on the y-axis, and then it's going to tend towards the oblique asymptote, which is what it has to do. That pretty much looks like it's going to cut the oblique, so let's try that again, and it tends towards the oblique. So really cool graph. I mean, that right hand side's a bit boring, it looks like a hyperbola, but that left hand side, man, that's fun. Really cool. Again, no idea that this is what it was going to look like. You kind of just start and plot your points and then see what makes logical sense. Okay, last one for this video. This is now exercise 9, sorry, example 9, and that's f of x. And so let's have a look. This is now a quadratic divided by a quadratic. Interesting. We haven't drawn those before. So my first thing is, can I simplify? And so I'm going to factorize the top. So f of x, this would equal x plus 3, x minus 2, and the bottom will be x minus 3 squared, which is x minus 3, x minus 3. So does it simplify? No, it doesn't, but it does give me a little bit of information, because from that I can see that my vertical asymptote is at x is equal to 3. I can also see that I have intercepts. I haven't found my oblique or my horizontal asymptote yet, but just because I factorized, I can see my x-intercepts are at -3 and 0 and 2, 0. While I'm there, let's write down my y-intercept. If I made x equal to 0, I'd probably go to the original graph, because then that's 0, 0, 0, 0. I get -6 over 9, which is -2 over 3. And I know that this is going to have a horizontal asymptote because the degrees are equal to each other. Now don't forget, if the degree at the bottom is equal to or bigger than the one at the top, there's a horizontal asymptote. Now I could go and find the limit as x tends to infinity of this function. However, if that's not the question, if I'm just trying to draw here, I can use the shortcut. Now what was the shortcut? The shortcut was, if these degrees are equal, the limit just basically becomes the ratios of their coefficients, which here is 1 to 1. So if you've done this long enough, you know the answer is y is equal to 1. If you're a little bit rusty on that, don't forget that you take x squared plus x minus 6 all over x squared minus 6 plus 9, and you're trying to take the limit as x tends to infinity. So what you do is you divide the top and the bottom by the highest degree, so you divide by x squared. So this is 1, and this is 1 over x, so that'll tend to 0, that'll tend to 0. And this is 1 minus, that'll tend to 0, and that'll tend to 0. And that's why, because they're matching degrees, it's that ratio that remains. And so I get y is equal to 1. I wouldn't have to show any working if this was, just a drawing question. Okay, finally, I need some stationary points. Now, this is probably the only really tricky part of this. So let's find my stationary points by finding my derivative and setting equal to 0. So my derivative of f, pardon my typo, my f dashed x is differentiate the top. So that's 2x plus 1. Leave the bottom. X squared minus 6x plus 9 minus, might need to erase this for space, pardon me, so minus, leave the top, so x squared plus 6 minus 6, differentiate the bottom, 2x minus 6, all over the bottom squared, even though we know that bottom is simply going to become discarded in a moment. So the moment I make this equal to 0, I'm going to discard the bottom. So a little bit of multiplying out, so I get 2x cubed minus 12x squared plus 18x plus x squared. Of course I could do this faster. Minus 6x plus 9. Now it's minus 2x cubed plus 6x squared minus 2x squared plus 6x plus 12x and minus 36. So a little bit annoying. Possibly should have done some of those in my head. So 2x cubed minus 2x cubed, at least that makes our life easier. So now my x squareds, 12x squared plus x squared plus 6x squared minus 2x squared. So that's minus 11x squared minus 5x squared minus 7x squared as far as I know. So let's say minus 7x squared. Hopefully I'm not making mistakes here. 18x plus 6x plus 12x and minus 6x. So it basically becomes 30x. Again, hope I'm not making mistakes. And finally, let's use a different color. 9 take away 36 is minus 27, I think. Okay, now if I've got this right, I just plug that into my calculator. I definitely don't show any working, so I just use my function mode on my calculator, and I get x is equal to 3, or x is equal to 9 over 7. Now 9 over 7, if you change to a decimal, is 1,29 roughly, and then something. Now notice this is interesting. I know that x can't equal 3 because it's the vertical asymptote. Now notice, this is the second time this has happened. If we have a repeated asymptote, we notice that one of the stationary points ends up being the asymptote. So that's pretty cool. So actually there's only one stationary point here, which is 1,29. If I substitute that back into the original formula, I can figure out my y value. I did that and I got minus 1,04. Now again, this seems very interesting. I'm not too sure I would work out any points of inflection just yet. I'm going to try and sketch what I've got so far, and let's see how it goes. So what do I have so far? I have a vertical asymptote at x is equal to 3, and I have a horizontal asymptote at y is equal to 1. So let me put those in first. Then I have an x-intercept, and my x-intercepts, as far as I remember, I don't remember, so let's go up, negative 3 and 2. So that's at 3, so 2 would be, let's say, around about there, and negative 3 would, let's say, around about there. Okay, so the only thing I haven't really got on here is that stationary point. That stationary point existed at 1,29, so if that's 1, 1,29 slightly above that, and negative 1,04, so slightly below that. So this is 1,29 and negative 1,04. Now, I think it's pretty obvious that this particular stationary point has to be a local minimum, because if I have to turn and go through 2, but I have to be stationary and still go through negative 3, I'm pretty much turning there. Now, I have to tend towards my vertical asymptote, and so we've never really seen this before, but if this has to be a stationary point and I have to go through 2 and tend towards my vertical asymptote, what? It looks like my graph is going straight through the horizontal asymptote. Now, is that allowed? Well, if we're allowed to go through a oblique asymptote, there doesn't seem any reason why we can't go through a horizontal asymptote. Don't forget that a horizontal and oblique asymptotes are asymptotes that the graph tends towards as x tends to infinity and negative infinity. So it's not that x can't be that or y can't be that. Now, unfortunately, if it goes through, we need to label that point. So I'm going to have to label that point in a moment, and we'll discuss how we're going to do that in a moment. Now, if this is a stationary point, I'm going to have to be stationary. I'm going to have to go through that and then tend towards the asymptote. So again, very interesting function. I didn't know it looked like that, but that's the only thing that makes sense, because I have to tend to the horizontal asymptote as x tends to negative infinity. Now what happens on the other side? What is happening here? Absolutely no idea. Now I have to be tending towards the asymptotes, which leaves me with two kind of possibilities. There's no intercepts, so I cannot possibly have a graph there. Why am I drawing a hyperbolic type shape? I'm drawing that because I'm tending towards the asymptotes, and so that's pretty much what it has to look like. Can't have that because of the intercept, and that intercept didn't exist. I can't have a stationary point because that didn't exist here, and so this graph is not allowed to turn at all. And so I'm pretty convinced that I have to have that type of shape. If you wanted to be certain, you could just add in, substitute in 4 into the original graph and check that that is a value above 1. So you could plot that point, but it's not, pretty much that's the only option for it. Now, I do need to label this point here. Now, this is where the graph equals 1. Now, what was the graph? The graph was x squared plus x minus 6 all over x squared minus 6x plus 9. Now, I need that to equal 1. So basically, x squared plus x minus 6 is going to have to equal x squared minus 6x plus 9. So my x squareds actually disappear. I get 7x equals 15, and I get x is equal to 15 over 7, which is, 2 comma something. And that looks very plausible. That's 2 comma something. The asymptote is at 3. So that's entirely plausible. So what's this point? This point is when x is 5 over 7, y will be 1. That's that point there. And now that's pretty cool. We hadn't actually seen that before, so that's quite fun. Again, what a cool graph. Who would have known that it looked like that? Don't be panicked if you don't know what it looks like. You just kind of figure out what it's forced to look like based on the evidence given to you. Don't forget to label the points where any graph goes through an asymptote. Okay, now we have 2 more examples to go in terms of sketching, but I do think that this video is long enough, so let's end it there, and I hope that was a lot of fun, because I find these awesome. Cool.